So we've looked before at a sample of gas, and we've seen that while there's an average velocity, when you look at all the gas particles, they are moving at a variety of speeds. So a person named Maxwell, James Maxwell, came up with an expression that is known as the Maxwell distribution. And what this does is it shows for any particular speed how many molecules out of the total are moving at that speed. So we'll look at that graph on the next slide. Okay, so for this one, we're actually looking at oxygen at two different temperatures. So in the red, let's see if I can, there we go. So here, this is a graph for the Maxwell distribution for oxygen at 25 degrees. And the height then is related to how many molecules out of the total have that particular speed. So the most common, or the average speed for oxygen at 25 degrees would be 400 meters per second. If we increase the temperature, and this is shown in the second graph, then what happens is the graph spreads out and moves to the right. So what that means is that there is a greater sort of range of possible speeds, and the maximum, which we originally had here, is a lot less. But most importantly, we have more molecules at a higher speed over on the right side. So this is a summary of what we just said, that you can plot the number of particles versus the speed, and it gives you the most probable speed, which is the peak, and it also shows what happens when you increase the temperature. Basically, you change the distribution. So let's say we have a situation like this. We have two containers. B has twice the volume of A, and the green circles represent HCl. Let's see. Yeah, and the red circles represent helium. Okay, so you have these two containers, and you want to compare various properties based on what you know here. So you know that the volume of B is twice that of A, and you know that each sphere represents a mole, and you also know that the temperature is the same for both of them. Okay, so for the first question, it says compare the pressures of the gases in the two containers. So you can wait for a second and try to do that. Hopefully you said that the pressures were the same, and the way that you figure that out is that when you look at PV equals nRT and you solve for pressure, temperature is the same, R is the same, and the ratio of NV is the same because you have 2 moles of HCl, but that's in a volume that's half that of B, where you have 4 moles in twice the volume. So the pressures are the same. Next, you want to compare the densities. So for that one, you are looking at 2 moles of HCl at 36.5 grams per mole. And for the helium, you're looking at 4 moles, and that's times 4 grams per mole. So that would give you a total of 16 there. And even though it's in, no, not even though, it's less mass, and it's in twice the volume. So that's going to be the lower density. The number of atoms in the two boxes. So in the right-hand side, you have 4. And in the left-hand side, you have 2 moles, but each mole is 2 atoms, so that's also 4. Okay, next you want to figure out what would be the mole fraction if you transferred all the HCl in A to box B. So I'll let you think about that. Okay, so you'd have a total of 6 moles in B, and 2 of those moles would be HCl. So that would give you a mole fraction of about 1/3. And finally, which of the two gases effuses faster? So for that one, the lighter the molecule, the faster it effuses, so the answer to that one would be B.